Hey, welcome! So today we're going to talk about something you use literally every single day, but probably never really think about, our numbers. And trust me, this is not just about counting. It's an incredible story of human ingenuity, of crisis, and of pure logic that basically built the world we live in. All right, let's get into it.
The best way to think about this is to see math as its own language, a language that we've been building for thousands of years to try and make sense of reality. And like any language, it all starts with the alphabet. For math, that alphabet is numbers. But here's the thing, this alphabet didn't just fall out of the sky. We had to invent it, piece by piece.
You know the numbers we use today? The whole base 10 system with the symbols 1 through 9, and of course that game changer 0? Well, that system has a really cool backstory. It all started with Hindu mathematicians way back around 600 AD. Then, in the 8th century, it traveled to Baghdad's famous House of Wisdom, where it got translated into Arabic. From there, it slowly, and I mean slowly, made its way through Western civilization, eventually kicking older, way clunkier systems like Roman numerals to the curb. And this new Hindu-Arabic system, it was a revolution.
So if we're telling the story of this language, where do we start? Well, we start at the very beginning, with the first thing humans ever really needed numbers for. Just plain old counting.
And that brings us to our first set of numbers, the absolute foundation, the natural numbers. You know these, they're the ones you learn first. 1, 2, 3, 4, and on and on and on forever. They're simple, they're intuitive, they're just the numbers for counting stuff.
Now, these natural numbers have a really neat feature, which mathematicians call the closure property. It sounds kind of fancy, but the idea is super simple. It just means if you take any two natural numbers and add them, what do you get? Another natural number. Same with multiplication. You can add and multiply forever, and you will never, ever leave the world of natural numbers. It's this perfect, self-contained little universe. But it turns out that universe was way too small.
See, the whole history of our number system is basically a story of running into problems we can't solve and then having to invent new numbers to get the job done. We kept hitting these walls and realizing the numbers we had just weren't cutting it anymore. We had to expand our alphabet.
So for instance, take a look at this equation. It seems simple, right? Some number plus 5 equals 2. But think about it. If the only numbers you have are the positive counting numbers, 1, 2, 3, and so on, this is literally impossible. There's no natural number on Earth you can plug in for x to make that equation true. We'd hit a dead end. Our number system was broken.
So what was the fix? We invented more numbers. This is where the integers come onto the scene. You take all the natural numbers, you invent their negative opposites, and then you add in the truly revolutionary idea of 0. And just like that, problems like x plus 5 equals 2 aren't impossible anymore. The answer is just -3. We made our number language bigger to solve the problem of subtraction.
So, great. Our world of numbers is bigger now. It's more powerful. We can add and subtract whatever we want. But we almost immediately hit another wall. What about an equation like this? 5 times some number equals 3. If you're only allowed to use whole numbers, the integers, you're stuck again. There's no integer that solves this. We found another gap in our system.
And to fill that gap, we took the next big leap and came up with the rational numbers. Basically, any number that you can write as a fraction, one integer over another. And bam, the equation 5x equals 3 suddenly has an easy answer, 3/5. Now at this point, you'd think we were finally done. I mean, we've got positives, negatives, 0, and all the fractions you could ever want in between. What else could there possibly be? And for a long, long time, people, especially the ancient Greeks, thought that was it. They believed that rational numbers, fractions, could describe absolutely everything. But then they stumbled onto a discovery so weird and so upsetting that it literally triggered a full-blown crisis in mathematics. And the problem didn't come from some complicated equation. It came from something incredibly simple, a square. Just imagine a perfect square, where each side is exactly 1 unit long. The Pythagorean theorem tells us that the length of the diagonal squared has to be 1 squared plus 1 squared, which is 2. So the length of the diagonal itself must be the square root of 2. The big, scary question was, what number is that? The Greeks just assumed it had to be a fraction. It had to be. But they were very, very wrong. And this right here is the heart of the matter. Rational numbers, when you write them out as decimals, do one of two things. They either stop, like 1/2 is 0.5, or they repeat a pattern forever, like 1/3 is 0.333. But this new number, the square root of 2, was a totally different beast. Its decimal went on forever and ever without repeating. There was no way to write it as a simple fraction. It was a new kind of number, an irrational number.
So think about the number line for a second. If you could plot every single fraction, every rational number, you'd think that line would be totally solid, right? Completely filled in. But it's not. The discovery of the square root of 2 showed us that the number line is actually full of these microscopic holes, these gaps between all the fractions. And hiding in those gaps are these mysterious irrational numbers, like the square root of 2 or pi.
So how could they be so sure? I mean, how do you actually prove that a number can never be written as a fraction? Well, the Greeks came up with one of the most beautiful, most elegant arguments in all of human history. It's called a proof by contradiction. Let's just walk through it real quick. It's brilliant.
Okay, so check this out. First, you start by assuming the exact opposite of what you want to prove. Let's just pretend that the square root of 2 is a rational number, that we can write it as a fraction, p over q, in its simplest possible form. Okay? Well, a little bit of algebra shows that if that's true, then p squared has to be an even number, which means p itself has to be even. So we can write p as 2 times some other number, let's call it m. Now, if you plug that back into our equation, you find that q squared must also be even, meaning q is also an even number. And right there, that's the fatal flaw.
That's the contradiction. If both p and q are even, it means our original fraction wasn't in its simplest form, because we could have divided both by 2. But our very first step, our core assumption, was that the fraction was in its simplest form. So because our starting point led us to a logical impossibility, that starting point has to be wrong. The square root of 2 cannot be a rational number. It is, provably, irrational. All with pure logic. It's amazing.
So this shocking discovery actually ended up giving us the complete picture. It taught us that to have a number system that doesn't have any holes, we needed to combine both types of numbers, the rationals and the irrationals. And that finally brings us to what we call the real numbers. It's the set of all the rational numbers plus all the irrational numbers. When you put them all together, they plug all those gaps, and you get the smooth, unbroken, continuous number line that we all know and use today. And this leads to a really profound idea. With the real number system, we finally have a perfect one-to-one match between the world of numbers and the world of geometry. For every single point on that line, no matter how small, there is a real number that corresponds to it. And for every real number, there's a point on the line. The system is finally complete, no more gaps.
Which leaves us with one final, kind of mind-bending question. Think about it. We built this whole incredible structure. Natural numbers, integers, rationals, irrationals. We invented this entire language just to solve logical puzzles that we ourselves created. So why? Why does this system, born from our own minds, also happen to be the language of the universe itself? Why does it so perfectly describe everything from the spin of a galaxy to the behavior of an atom? Now that is something to think about.